What is the main motivation behind the development of LVLM-Intrepret?
The main motivation behind the development of LVLM-Intrepret is to address the challenge of hallucination in large vision language models, LVLMs, by providing interpretability tools for interactive analysis. The goal is to better understand the reasoning behind model responses, particularly in the context of LVLMs that integrate visual understanding. The application aims to adapt multiple interpretability methods to LVLMs, such as raw attention, relevancy maps, and causal interpretation, to help mitigate hallucination and improve model transparency. By offering insights into the inner workings and failure mechanisms of LVLMs, LVLM-Intrepret seeks to enhance the interpretability of these models and strengthen confidence in their predictions and behavior.
Can you explain the phenomenon of hallucination mentioned in the introduction of the paper?
The phenomenon of hallucination mentioned in the introduction of the paper refers to the fabrication of untrue information by large language models, LLMs, and large vision language models, LVLMs. These models, such as GPT and LLaMASC, have demonstrated remarkable understanding and reasoning capabilities, but they are still prone to generating outputs that contain false information. This phenomenon of hallucination is a significant challenge in these models, including LVLMs, and may be exacerbated by the addition of visual information. With the increasing number of parameters in LVLMs, interpreting and explaining model outputs to mitigate hallucination is becoming a growing challenge. The paper introduces an interpretability tool, LVLM-Intrepret, to address this issue by adapting multiple interpretability methods to large vision language models for interactive analysis, including raw attention, relevancy maps, and causal interpretation. These methods aim to help users better understand the inner workings of LVLMs and identify the sources of hallucination in model responses.
How does LVLM-Intrepret aim to address the issue of hallucination in large vision language models?
LVLM-Intrepret aims to address the issue of hallucination in large vision language models by providing interpretability functions such as raw attention visualization, relevancy maps, and causal interpretation. These functions allow users to better understand the inner workings of the model and identify the specific parts of the input data that contribute to the model's generated output. By visualizing raw attentions between image patches and tokens, users can gain insights into how the model attends to the image when generating each token, helping to identify potential areas of hallucination. Relevancy maps assign local relevancy scores to elements in the input based on their contribution to the output decision, aiding in model debugging and providing explanations for inaccuracies by pinpointing the most relevant parts of the input to the generated output. Causal interpretation, through methods like CLEANN, helps in deriving causal explanations from attention in neural networks, allowing users to understand which input tokens influence the model's output tokens, thus helping to mitigate hallucination by identifying and potentially correcting erroneous associations made by the model.
What are the interpretability methods adapted to large vision language models by LVLM-Intrepret?
The interpretability methods adapted to large vision language models by LVLM-Intrepret include raw attention visualization, relevancy maps, and causal interpretation. LVLM-Intrepret allows for interactive visualization of raw attentions, enabling users to investigate interactions among tokens from each modality. Relevancy maps are designed to enhance interpretability by illustrating the relevance of different input components to the model's output decision. These maps assign local relevancy scores to elements in the input based on their contribution to the output. Causal interpretation involves deriving causal explanations from attention in neural networks, where explanations tokens influence the model's output. LVLM-Intrepret employs CLEANN to explain large vision language models by learning causal structures over input-output sequences of tokens, identifying the parts of the input that influence specific model outputs.
How does LVLM-Intrepret utilize raw attention for interpretability analysis?
LVLM-Intrepret utilizes raw attention for interpretability analysis by allowing users to interactively visualize the interactions among tokens from each modality. The application enables users to investigate the average attentions between image tokens, query tokens, and answer tokens, providing insight into how the model attends to the image when generating each token. Users can select tokens from the generated response to visualize the average attentions between image patches and selected tokens, as well as select image patches to visualize how each output token attends to specific locations in the image. This functionality helps users better understand the global behavior of raw attentions within the large vision language model, facilitating the interpretation of model outputs and the reasoning behind the generated responses.
Explain the concept of relevancy maps and how they are used in LVLM-Intrepret.
Relevancy maps in LVLM-Intrepret are used to enhance interpretability by illustrating how different components of an input, whether text or image, are relevant to the model's generated output. These maps assign local relevancy scores to each element in the input based on their contribution to the output decision. The calculation of relevancy maps is adapted to LVLMs like LLaVA by backward propagating relevancy scores through the LLM and the vision transformer used as the vision encoder. For image analysis, the relevancy scores corresponding to image patches are reshaped into a grid matching the original image layout, forming the basis of the relevancy map. This map is then upscaled to the original image size using bilinear interpolation, visually representing the most relevant parts of the image to each generated token. Relevancy maps aid in model debugging, ensuring fairness and providing explanations for inaccuracies by identifying the parts of the input most relevant to the model's output.
What is the significance of causal interpretation in large vision language models, as discussed in the paper?
The significance of causal interpretation in large vision language models, as discussed in the paper, lies in its ability to provide explanations for model outputs by identifying the specific input tokens that influence the generation of certain output tokens. This method allows for a deeper understanding of how the model makes decisions and what parts of the input data are crucial in determining the final output. By employing causal interpretation, the paper aims to uncover the causal relationships between input and output tokens, enabling users to pinpoint the exact elements in the input data that lead to specific model predictions. This approach helps in making the decision-making process of large vision language models more transparent and interpretable, ultimately enhancing the trust and confidence in the model's predictions. Causal interpretation also aids in model debugging, ensuring fairness and providing explanations for inaccuracies by identifying the most relevant parts of the input to the generated output. It allows users to manipulate the input tokens to observe how changes impact the model's output, thereby facilitating a better understanding of the model's inner workings and improving its overall performance and reliability.
How does LVLM-Intrepret enable users to interactively visualize raw attentions among tokens from each modality?
LVLM-Intrepret enables users to interactively visualize raw attentions among tokens from each modality by allowing them to investigate the interactions among tokens from each modality through heat maps that show average attentions between image tokens and query tokens as well as answer tokens. Users can select tokens from the generated response and visualize the average attentions between image patches and the selected tokens to understand how the model attends to the image when generating each token. Additionally, users can select image patches and visualize the degree to which each output token attends to that specific location. This interactive visualization of raw attentions provides insight into the global behavior of raw attentions, and helps users better understand how the model processes information from different modalities to generate its output.
Can you describe the interface and functionality of LVLM-Intrepret as presented in the paper?
LVLM-Intrepret is an interpretability tool for large vision language models that offers multiple interpretability methods for interactive analysis. The application was developed using Gradio and follows a standard layout for multimodal chat. Users can upload an image and issue multimodal queries to the LVLM through the user interface. Additionally, there is an editing feature that allows for basic modification of the input image to probe the model with adversarial variations. As the LVLM model generates a response, the attention weights of the model are stored internally and later presented to the user for visualization. The application also constructs relevancy maps and causal graphs relating to the output of the model. Users can utilize these results to interpret the model output. LVLM-Intrepret allows for interactive visualization of raw attentions, enabling users to investigate the interactions among tokens from each modality. Relevancy maps are designed to enhance interpretability by illustrating how different components of an input are relevant to the model's generated output. Causal interpretation is also provided, allowing users to understand which input tokens are responsible for specific output tokens by learning causal structures over input-output sequences of tokens. The tool aims to complement domain-specific solutions, improve existing and future large vision language models, and enhance confidence in the predictions and behavior of these models.
Based on the case study mentioned in the paper, how does LVLM-Intrepret analyze the impact of text and image tokens on the output generated by LLaVA model?
LVLM-Intrepret analyzes the impact of text and image tokens on the output generated by the LLaVA model by calculating relevancy scores for each generated output relative to the input features to LLaMA, focusing on the LLaMA self-attention layers. The tool observes instances where LLaVA predominantly attends to the text tokens over the image tokens, as indicated by lower relevancy scores assigned to the image tokens compared to the text tokens. In cases where the model shows less attention to the image tokens, it becomes more vulnerable to manipulation, potentially altering its responses based on the query with less consideration for the image content. This behavior is illustrated in the truck scenario depicted in the paper. Conversely, when the generated outputs demonstrate a higher relevance to the image tokens than to the input text, the accuracy of LLaVA seems to remain consistent regardless of how the question is formulated, as shown in the examples provided in the paper. LVLM-Intrepret thus provides insights into how the model prioritizes and utilizes text and image tokens in generating its outputs, shedding light on the factors influencing the model's decision-making process and response accuracy.